Okay, so today we're going to start our first lesson in modern physics, and we're going to learn about the discovery of electrons and of photons. So this first lecture is going to be about electrons, and then the second lecture will go into photons. So in the previous unit, we were looking at the wave properties of light. So we studied reflection, diffraction, interference, okay, which are all wave properties. And we looked at experiments that proved that light had wave properties, okay. Modern physics really began in the late 1800s when we discovered the electron, okay, and that is what is led to the science of particle physics, and we'll see how that has led to quantum physics. So we're going to talk about how we discovered the electron and how we came to a more full understanding how we discovered the charge and mass of an electron. And also in the next lecture I'll talk about photons, which are essentially particles of light. So in chemistry class, you learn about the history of atomic theory. And John Dalton had an atomic theory as of the 1800s, the early 1800s. And two parts of his atomic theory stated that, all matter is composed of tiny, indivisible particles. So he didn't know about subatomic particles, protons, neutrons, and electrons. He thought that atoms were just sort of solid spheres. Okay, and then he thought atoms differed and we had different elements. We knew about different elements, and so he thought those atoms were different for different elements, but he really wasn't sure how. Okay, so along came J.J. Thomson in the late 1800s, and in 1897 he conducted an experiment with cathode ray tubes. And this is a picture of him here with his apparatus that he did some of his research with. So a cathode ray tube is essentially a glass tube that has an electrical source on either side of it. And you pull all the air and create sort of a vacuum chamber inside of the tube. And when you turn on the electrical source, you get a ray of fluorescent light that is passing through the tube. So let's kind of look at a video here. Okay, so there you can see, the fluorescent ray that is going through this glass tube. And so we kind of discovered that this could happen, just in playing around with electricity. And what J.J. Thomson did was he started to apply electric fields here and here, or an electric field that went, through the glass tube, and also magnetic fields. And as he did this, the ray was deflected. So you can see here in the video they're going to show it with a magnet. Okay, so when the magnet comes close, you can see that the magnetic field causes the ray to be deflected. Now, how did we know what the charge was? Well, when you use an electric field, if we have the positive plate and a negative plate here, as in a parallel plate, that is going to make an electric field, if the light is going to deflect and bend towards the positive end, we know opposites attract, and therefore that it had to be made up of negative electrons. Okay, so based on this experiment, he was able to determine the charge to mass ratio. And so let's look at the physics, the math of how he was able to determine the charge to mass ratio of an electron. Okay, and this will look familiar, a little review from electricity and magnetism. Okay, so essentially what we have here is a uniform magnetic field. Okay, the X is representing a magnetic field into the page. And if we are to shoot electrons straight through, so that's the cathode ray, the electrons coming right here, and we use our right-hand rule, we know that the force, as soon as it enters, is going to be straight down, and then as it turns with it. Okay, and to get the magnitude of that magnetic force on the charge, we take the charge times the velocity of the charge times the strength of the magnetic field. Okay. We also know that because the force is perpendicular to the velocity, it causes the object to turn in an arc or in a circle, which is a centripetal force. And we know centripetal force is mv squared over r. So if we set these forces equivalent to one another, that is how we are able to derive the charge to mass ratio, simply by measuring the arc path and knowing the strength of the magnetic field. J.J. Thomson was able to figure out the charge to mass ratio. Okay, so, but he didn't know the charge or the mass independently of one another, he just had the charge to mass ratio. So Robert Milkins' oil drop experiment was about 10 years later, and he devised a way to actually calculate what the charge of an electron was. And since we have the charge to mass ratio, if you have the charge, then we can also calculate the mass. So here you can see this is actually his apparatus that he used, and let me make it a little bigger so that you can see the animation of it. Okay, so here is the apparatus, and you can see that here is a microscope viewing, so he was watching what was going on in this chamber. And here he has this little bulb. Essentially, if we look over here on the animation, you can see inside of the chamber. You have a bulb that aerosolizes oil. So you have these tiny little oil droplets, and when they fly into the chamber, gravity causes them to fall down into the viewing area where the microscope is, and you can watch them go past. Now, because the oil droplets are so tiny, okay, they hit terminal velocity very fast. So friction is not negligible. Friction is acting against the, air resistance is acting against the oil droplet as they're falling down, so they come to equilibrium and they travel downwards at a constant velocity. Okay, let's go ahead and look. I've got a cool animation of to see actually what they saw in the chamber through the microscope view. So it's right here. Let's go up. Okay, so this here is supposed to be the field of view of the microscope. So if I hit the spray button, this is like me squeezing the bulb, and you can see that the oil droplets start to fly upwards. Okay, why are they flying upwards? Last time I checked, gravity caused things to fall down, right? Not fall up. Well, it's a really simple answer. You're looking through a microscope. A microscope is made of a lens, and as we learned in the last unit, converging lenses cause inverted images. So you're basically looking at what's happening upside down. Just like in a microscope, if you're looking at biology class and you move it one way and it goes the other in your field of view. Okay, so all of these dots represent the oil droplets, and they all travel at different velocities because your velocity is dependent on your mass. Your terminal velocity is dependent on your mass. And so every single one of them, they're not uniform oil drops, they're all different sizes. So they are achieving terminal velocities at different velocities. Okay, now if I'm to apply an electric field, okay, that's what this area is supposed to mimic. Here, let me turn the voltage all the way down, make sure it's down. Okay, so I hit another drop. If I apply an electric field, that should cause some of these droplets to stop based on what charge they have. So if I turn my electric field on, I can try and add voltage until I essentially suspend an oil drop. So if you look right here, that oil drop is essentially like suspended there. Okay, it is in equilibrium. Okay, so, and it's flying a little up. Let me see if I can turn the voltage up a little bit to keep it from moving. So it's suspended there, and it's in equilibrium. So in this case, gravity is equal to the electrical force. Okay, so how can I calculate this? If I scroll down, you can see we have this equation. And let's just go back and review a little bit of our electricity and magnetism. We know this is force due to gravity, mg. But remember that electrical force is equal to Q times the electrical field that it's in. Okay, and the electrical field, or the uniform electric field in between the parallel plates, is equivalent to the voltage between the plates divided by how far apart they are, so V over D. Okay, so that gives us sort of measurable things. But the problem with this equation is we still have mass, right? If we still have mass, we can't calculate Q independently. So we have to somehow figure out what the mass of those oil droplets are. Okay, and relate it to the charge. So what he did then was, oh, you see my dot's been moving a little bit, okay, is he would turn on X-rays, and you can see here in this, and down here, there's X-rays applied. And as you turn on the X-ray, it causes the electron that, or the oil droplet then to move, because you have, let me turn these rays off because I'm still removing electrons. Is he going to escape from me? Yeah, he's going to escape. Let me spray some more. So basically what we've done is with radiation, we've caused electrons to bounce off of this oil droplet, okay? And as it's bounced off the oil droplet, okay, we have then changed its charge. But we know that an electron is relatively so massless that it doesn't really affect the overall mass. So by removing electrons and then being able to, calculate the terminal velocity of one of these droplets, we use the terminal velocity to know the mass. And then we have our equation here, which will allow us to determine the charge. And this is how we discovered the charge of an electron. And the charge of an electron is negative 1.6 times 10 to the negative 19th coulombs. And that's on your reference tables. Now, we also had the charge to mass ratio because of J.J. Thomson's experiment, so using what we now knew was the charge, we could also use the ratio to find the mass, which is 9.11 times 10 to the negative 31 kilograms. So that's how we discovered the properties of an electron and that an electron existed. In the next video, we're going to discuss photons.